seal it right up. All right, so today, so last time we did the transition equation. So that's the horizontal axis of the spectrum, where we have the lambda 1 to 2 and lambda 2 to 3 and lambda 3 to 4. So that's where we have where the transitions occur along the horizontal axis of a spectrum. If we're doing it by wavelength, if we're doing by frequency, we had the frequency transition equation too. So everybody needs to think about these equations. It's really a lot of this is just vocabulary. The transition equation is that equation for the differences in energy levels. So that's the horizontal axis. That's where the transitions occur. Today we're going to solve the intensity equations. Okay, and those have the word transition too, but it's transition dipole moment. So the word moment is in there. And that's just a mathematical multiplication of these waves. Okay. So in order to do spectroscopy, it is the interaction between light and matter. And so there are some criteria to have. If we have a non-charged particle like a neutron, then light will go right past it. There's nothing on a neutron or in a neutron that light can interact with. Okay, so a neutron is an example of what we would call dark matter. Okay, it doesn't interact with light. So when they talk about the universe and they add up the mass because they know the masses of the stars from their brightness and so on, and they're like, well, what's holding all this together? They hypothesize that there's a black hole in the middle. They don't see the black hole. Now we see the horizon, the light horizon of black holes. But except for the last few years, we haven't been able to see a black hole. Okay, but we know it's there because of the gravity. It's just like that Star Wars scene where she's like, go to the center of gravity's pull and you will find your planet. You know, and y'all know that from the prequels? Yes. Qui-Gon's lost his planet. Okay, so if we have a charged particle, then we have an oscillating electric field, we're in business. So oscillating electric field, charged particle, we can have interactions. And that particle we're going to describe as a wave. So it's a wave that's charged, if you will, but it's hard to think of a charged wave. We think of a charged particle, but we have a wave function. Light comes in, it's an electric field. It's going to interact with that wave function. And then the integral now with the other wave function is non-zero, perhaps. If it's zero, there's no probability of jumping, but if it's non-zero, that interaction with the other states is non-zero, then we could have a probability of jumping those energy levels if the light energy matches that energy difference. So these are the requirements for spectroscopy. We have to have some interaction with an electric or magnetic field. So light has a magnetic moment too. It's about 1,000 of the strength of the electric field. Well, most of the time we're just dealing with the electric part of electromagnetic radiation. It has to have an unequal population of energy levels. That's the Boltzmann piece. So if we're dealing with the ground state and we're at a low enough temperature that there's very little excitation, then we can have absorption. Okay. And then it needs to have a significant probability for the transition, and that's that transition dipole moment integral, this I piece. So we're going from n to n prime, and we will do the integral today to show that probability for the transition. So here's all the possibilities just for 4 quantum states. So we saw for the wave function last time. And so we have our first four wave functions, and we could have delta n equals 1. So we could go from 1 to 2, 2 to 3, 3 to 4. But what if we had delta n equals 2? We could go 1 to 2, 1 to 3, and then 3 to 4. And of course, if we had more wave functions, we'd have more arrows, but this is the first 4 transitions. If we had delta n equals 3, notice delta n is 3, so we're going from 1 to 4. So we have these possibilities. I'm not going to say they're probabilities. We're going to solve for the probabilities, but they're at least possible at this point. Okay. And then we also have the emissions. If we have particles that are excited, we'll get emission. But in this situation, we've got the particles here, and this is the Boltzmann distribution. It's highest probability for the ground state, less probability for the excited state, and it drops off exponentially. That's the exponential function of the energy difference divided by kT. And so it drops off rapidly at low temperatures. We raise up that temperature, it drops off less rapidly. So here it was dropped off. Notice there's no particles in that fourth level. And so all of the emissions that start from level 4, even if they're probable, there's no particle there. So we wouldn't see it. So these are all the possible transitions, and even the Boltzmann distribution. Any questions about this? This is a really important mental picture right here. When we solve for light interacting with these wave functions and then integrating their overlap with the other wave functions, we'll see if the possible transitions are probable. Okay. And some of them will go to 0. So we have charged particles, check. We have unequal populations, check. And then we have the probability piece, and we've got to solve for that. So that's what we're going to do next. So transition probability is intensity, and it's proportional to 3 things. Remember, the absorption is equal to big. We have the line shape function. That's the widths of the peaks. We're going to ignore that for now. We're not going to deal with the Gaussian at this point. The number of molecules in the initial state are determined by the Boltzmann distribution. That's the unequal population piece. And then the probability piece is the square of the transition dipole moment integral. So we're going to do this integral where x is going to represent our photon of light coming in, the wave of light interacting with the initial state. So it's perturbing it in some way. And then we're seeing how that perturbed wave function overlaps with this one when they're multiplied by each other. And then if it's non-zero, but it could be negative, it could be positive, we're going to square that, and we're going to get all positive values, and we'll end up with an intensity that is related to this integral. Now, why the x-axis? We'll see that in a second. But we have this piece. So we're going to say the intensity is proportional to the Boltzmann piece times the integral of these wave functions with initial and final states here. We don't have complex wave functions in our example, but if we did, everywhere there's an I, we would change the sign on I. So that's what this little star is. It's saying the complex conjugate. We wouldn't change everything to negative or positive. We would just only change the sign in front of the imaginary pieces. So wherever there's an I, we would make it minus I. We're not going to have to deal with that, but I just want to explain what the star means. Okay. So these are our 2 pieces. Now, yes. The star, so this wave function, when we're coming in left multiplying, we have a wave function here that's complex, perhaps. Not in our example, but let's say we had, here we go. So maybe we have a wave function like this. Okay, would be equal plus I of v. But this is, with Euler's relationship, we can see that this is sine, I have to look this up, minus I. Maybe it's cos minus I. Does anybody remember? Can you help me out? And so if we have the complex conjugate of this, did someone look it up? I show you this expanded mainly to make the point that wherever there's an I, we change the sign, but that doesn't mean we change the sign everywhere. So this is not changing here. Only where there's imaginary I's can change. And that's the complex conjugate. And that's what we mean by this star. Okay. So that's that. And that's all just really going to be background for this course. So, if we were going, deep into quantum mechanics for all the different systems, like the hydrogen atom and everything, then we would really have to get into that. Another question though would be why X? This X in the middle. Well, I say it represents light, so let's think about why that is. So why do we use X to represent light? We want to get a maximum value for interacting with our wave function. And light's an oscillating electric field. It also has a weak magnetic field at 90 degrees. But if we take a snapshot of light at its maximum value, and in our system we only have one dimension, so what can we do for this electric field? We have to put it in that one dimension. So we're putting a field that has a positive and a negative pole on the x-axis. Well, that's the x-axis, right? The x-axis has positive values and negative values. And so if we put an electric field on that x-axis, we could call it E, or we could just call it X. It's X. So if we wanted to interact with our wave function, let's just use the x-axis and multiply it by our wave function. So it's sort of context matters. When X is in the middle here, it's representing light, h nu, right? Light. This is the wave function as a function of x, okay? The x-axis. So we have three functions. We have a wave function. Let's say we have the first excited state wave function, like this, and then we have the x-axis, like this, and then we have the ground state function, like this. And you see, we have three functions multiplied by each other. Can you see them? You see this diagonal line? I've sort of plotted this. This is, f of x equals x. Do y'all see that? Yeah. Just to kind of show, I don't know if that confuses you. It may confuse you, so, but anyway, that's the way I see it. And so we have this wave function, which if we didn't have this piece in the middle, if we just multiplied these two together, we verified this in the postulates lecture. This is equal to 0. So the first wave function times the second wave function integrated over all space, that's orthogonal, so it equals 0. So there's no overlap between those levels. But when light comes in, it interacts with this wave function, changes it some way, and now it's overlap with the second excited state, or first excited state is non-zero, and then we integrate over all space, we get a non-zero result, we square that, it's all positive, and now we have an intensity. Okay, so that's just some justification. So let's do this integral, and this is really done in the book, step by step with no skipped steps, okay? But we have this x, we have it times n plus delta n, and so on. And so we can multiply this through. And after 4 pages of calculus and algebra, which you can read yourselves, okay, we end up with this result. Okay. So then we end up with cosines. We have these pieces that came out of the integral. They look like they should have come out of the integral, right? We got this piece out here, and now it's in the denominator, right? So that looks like we've done some integration, and we have. Okay. And then we've got some cosines. And this is interesting. So we know from when we did orthogonality and the normalization of the wave function, we had the integer multiples of pi inside the sine function, and those were all 0. But this is cosine. So we need to pay attention, because sometimes they're +1, sometimes they're -1. So look here. This is in terms of pi. So when we get to pi, it's -1. When we get to 2 pi, it's +1. We get to 3 pi, it's -1. 4 pi, +1. So now we have a split between even and odd. So we have certain situations. So this one is cosine 0, which is always 1. Okay, but this is +1 when n is even, delta n is even, and this is -1 when delta n is odd. So we have an odd-even split. And this is where our selection rules come from. Okay. So if this is a result when it becomes -1, then we end up with -1, -1, so we end up with -2. If we have delta n equals even, we end up with a plus 1 here, and we have plus 1 minus 1, that becomes 0. And the same thing happens over here. When n is even, this piece goes to 0. And when n is odd, it equals plus 2. Okay. So here we end up with this. So we put in those values of even and odd delta n's, and so we have these. So both of these cancel out. They go to 0 when delta n is even. And then they equal this piece when delta n is equal to odd. Is an odd number, I should say. And so this is our intensities. So now this is great because we can calculate the intensities of our peaks. If I know the starting point, like if I'm starting in n equals 1 and I'm going up by delta n of 3, then I can put 3 here and 3 there. And if I know the box length, okay, notice what's not in here. Mass. So it's important to look at these intensities and say, oh, so the system mass doesn't depend upon the mass of the particle, but it depends upon the size of the box. Okay. Where's temperature? Well, that's in the Boltzmann equation. So this doesn't have any temperature dependence in it. Where's the spectral resolution, the width of the peak? Well, that's in the Gaussian. That's in the line shape function. That's not here. But our intensities do depend upon the size of the system. Okay. And so these are what we call our selection rules. It's where the intensity is non-zero. What do I mean by selection? Well, we have all those possible transitions, and we're selecting the ones that are non-zero. So the selection rules tell us which ones are non-zero. And so now we can look at this, and these are all the possibilities. And so for I think it's a minus 100 to plus 100 box, so a 200 angstrom box, these are the intensities that we get. So this is the 1 to 2 transition. You can see my terminology here. I'm just putting the quantum numbers in there. So from state 1 to 2 with x equals like, we get 1298. So it's a really strong peak, a strong possibility or probability there. But going from 1 to 3, that's a delta n of 2. And those aren't part of the selection rules. Those are the ones that are 0. So this is not allowed. We say it's forbidden. Okay. But this one is allowed. 2 to 3 is a little larger, okay? 15, 14. And then 3 to 4, 1576. So they kind of get more probable in terms of the higher excited states. But then we have the Boltzmann piece working against those. So they're kind of in competition. Notice emission, this is stimulated emission. They have the same one. So it doesn't matter if your 1s and 2s are switched. You get the same integral result, okay? So the emission ones, but the emissions are really harmed by the Boltzmann distribution. If you don't have molecules in that state, your emission intensity is going to be really small. You might have a huge integral that tells you it's really probable, but then you're multiplying by the probability of a particle even being there. And if that's a low probability, then your overall intensity is small. So hopefully you can see the thermal piece. Do I have molecules in that state? And then the wave function piece, which is this. This is the wave function piece. And then the 1 to 3, this is the delta n equals 3. So 1 to 4. And notice it's 8.3. It's still probable, but not nearly as strong as this. Okay. So these would be, we'll learn this terminology in a minute, but this is like the fundamental transition, the ground state to the first excited state, and then all of those others are hot bands. They only exist when the system is hot. And then this is an overtone, jumping multiple levels. So this one, interesting, it's probability of 0 because it's a delta n that is trying to change by an even amount. Absorption and emission probabilities are equal. These are things I've already said. And skipping levels is less probable. So we now have the transition equation piece, which also depends on the wave functions, but this is related to the energies. Okay, and now we have the intensity piece, the I piece. So we solved for this I piece just now, for the height of these things. So we did the transition equation in the postulates chapter, but here they are again. Okay, and so let's look at the transitions. If we're plotting these by wavelength, this is a big vocabulary page. So is there a star on this one? There should be a star on this one. Okay. This is the 1 to 2 transition. I thought I had these labeled. Let me see. Maybe it's the next one. Yeah. You can see that 1 to 2 transition. And then the next one is the 2 to 3. And then the 3 to 4. And the reason they're dropping off is because of the Boltzmann distribution. Okay? The I's by themselves would actually get a little bigger. But we're multiplying by the thermal population, and that's making it smaller. And so this is the 2 to 3, 3 to 4, 4 to 5, and so on. What are these? Well, those are the overtones. Those are the jumping by 3 levels. So this first one is 1 to 4. And then the next one is the 2 to 5. They both go up by 1. Okay. And then the 3 to 6. They're all delta n equals 3. What about the red ones? Well, those are delta n equals 5. 1, 3, 5, 7, 9. All of the odd transitions are possible, are probable. Probable. They're just not strongly probable. But they're there. You know, this is a 8.3 and that was a 1200. Okay. But this is a 1, so delta n 1 through 5. So this is a delta n of 5. So 1 to 6. And then 2 to 7. And then 3 to 8, 4 to 9. So those are big jumps, not very probable, but they're there. They can happen. We see some of these overtones in infrared. So if you have a really strong peak at the low frequency, you can see some small peaks at twice that frequency, and you'll see these overtones. Let's go back to the vocabulary. This is the fundamental. There's only one fundamental. So everybody write that down. There's only one fundamental peak. It's always the ground state to the first excited state. So the fundamental transition is the ground state up 1. If we're not in the ground state, we have to have some heat, some temperature. Those are hot bands. So anything not starting in the ground state is a hot band. So these red ones here are hot bands. And these ones that jump by more than 1 are overtones. Okay, so these are some good spectroscopic vocabulary. We'll see those in various techniques. And you'll see that in forensics too. You'll see some discussion of hot bands sometimes, or overtones. And this is what's going on. An overtone is always a jump of multiple levels. Yes? No, the molecule itself is hot, and it's in an excited state already. So I can't go from 2 to 3 without being hot, because I have to be in 2 to begin this transition. So temperature typically makes that possible. It's the Boltzmann distribution. If you're at a cold temperature, then you won't have any hot bands. And so think about this. This spectrum would really simplify if we cooled it down. We would only have the fundamental. Now we would have the fundamental first overtone. So the 1 to 4 transition, because it starts in 1. Okay. So we'd have that first overtone, but we wouldn't have any hot bands of the overtones. And we'd have the first one, the 1 to 6 transition. We would have that one. Because again, it starts in 1. So even at absolute 0, our molecules are going to be in the ground state, and we would have the true fundamental, the 1 to 2, and then these overtones, 1 to 4 and 1 to 6. But we wouldn't have any hot bands. So this second one here, that is got 2 terms associated with it. It's the hot band of the first overtone. So it's going from 2 to, let's see, I'm going by 1 to 4 and then 2 to 5. So this one's 2 to 5. So it's a hot band because it's starting in level 2, but it's also an overtone because it's jumping by 3. So it's going from 2 to 5. Okay. Notice what we get in plotting things by wavelength. Look how the wavelength plot really separates the fundamental. Okay, that's really nice. So sometimes we pick the horizontal axis to do certain work for us, and by wavelength we really separate those fundamentals. It's very nice. Okay, we could also plot this by energy. And if we plot this by energy now, energy and wavelength are inversely proportional to each other. So the horizontal axis has flipped. And now we see that these wavelengths are equally spaced. Not wavelengths, the energies are equally spaced. So 1 to 2 difference is going to be, if I go from 2 to 3 and 3 to 4, those are going to be jumping up by constant amounts. And so we'll have equally spaced peaks, but now this one is the fundamental. Because we're plotting by, do I have that? Yeah, this one is the fundamental. And those are the hot bands. Now plotting by energy is nice because I have that equal spacing and we can actually do a linear regression. If we pick those peaks, we can get the constants related to that equal spacing, that M and the L squared and all of that comes out front, which we'll see. Well, actually, you can see it up here. If we label those quantum numbers and we have a particular delta n, all the delta n's are 1 for this blue series, then the constant that comes out front is h squared over 4ml squared. And so that would be the spacing between these energy levels. And then we have the overtones. If we cooled this down, all the hot bands would disappear and we would just have the fundamental. And we would have this first overtone, the 1 to 4 transition, and then the 1 to 6 transition here. So what we do, let's see, typically, let's see, where's my algebra one? Here's all of the ones with the numbers put in for delta n's. Okay. So notice how they're labeled. 1 to 2, 2 to 3, 3 to 4, 4 to 5. A lot of times it's simple to just label them with the initial quantum state. So we would label it 1, 2, 3, 4, 5, and that's the delta n equals 1 series. Okay. And then this one we would label 1, 2, 3, 4, 5, 6, etc. But that would be the delta n equals 3 series. And this we would label 1, 2, 3, and this would be the delta n equals 5 series. We could just label them by those series. So here's an example from your laboratory that you're going to do. In the rho vibrational space. So this is a real spectrum. I think it's HCl. Yeah, I'm pretty sure it's HCl. And so we would label these quantum numbers as 1, 2, 3, 4, 5, 6, 7, 8, 9. And you might be able to get 13 and then 14. So you get all those peaks labeled. You pull their frequencies out, and those are the frequencies. They're the wave number values here. Okay, and so those are your Y values, those frequencies of those peak maxima. Okay, and we're looking at this equation. Well, this can be written as a linear equation. You know, Y equals mx plus B. And so if we do a trend line, or even better, a linear regression of this data, then we would get the slope and the intercept values. So we could fit to a linear trend using the linear regression tool, and we would solve for those physical constants. So the slope that comes out of that regression would be equal to h over 4mcl squared. If we knew the mass of the particle, we could solve for that L, and that would be related to the size of the system. And in a rotational system, that's the bond length of the molecule if it's a diatomic. If it's a bigger molecule, it's not the bond length, but it's the size of the molecule. So here's where we take spectroscopic information and pull out the physical constants. So even though we're dealing with a particle in a box, which is not really, not exactly a realistic system, you know, it's a simple one-dimensional system. It is related to realistic systems like HCl, which is a one-dimensional system. What's the bond length of HCl? You only have one dimension, R, the bond length of the HCl. And we could solve this. We could label this with quantum numbers, and we could solve for that size of that molecule. Now, it won't exactly, HCl won't exactly be this constant. It'll be the rotational constant, but it's very close to this. The point is, if you were to make that hydrogen, maybe a deuterium, where does that show up in this equation? It shows up in the denominator here. And so then these peaks should get closer together. If you make it a bigger thing, like let's say it now it's instead of deuterium, maybe we have chlorine bonded to an oxygen. Now we got an even bigger mass, and these peaks would get so close together that we wouldn't be able to resolve them, and so it would just be a mush. Would look like one peak, but inside that peak we have lots of individual rotational peaks. Let's look at other, like here's a nice mimic of a linear system, and let's look at the electronic structure. So we've gone into Gaussian, which we're going to learn later in this course, but I've calculated the electron wave functions for these polyacetylenes, starting with acetylene, then diacetylene, and then triacetylene. Okay, and so comparing that to the particle in a box, what do we expect to see? Well, we expect to see a wave function with no nodes to be the ground state. And sure enough, that's the ground state. So that's very similar to this wave function here with no nodes, right? So like if we were looking at this one, this has got 1, 2, 3, 4, 5 nodes. Notice how n equals 2 here has 1 node. N equals 3 has 2 nodes. So it looks like the quantum state is, quantum state minus 1 is the number of nodes, okay? Or the quantum state tells you how many of these lobes you have. You have 1, you have 1, 2, and then 1, 2, 3. And so here we are at 1, 2, 3, 4, 5, 6, and we have 6 of these lobes. 1, 2, 3, 4, 5, 6. So even though this is not a one-dimensional system, and it's super complex with these electron cloud, we see the same kind of behavior. What if we increase the box? Let's look at our equation here, the energies. The box is in the denominator. The size of the system is in the denominator. Oops. So what do we see here? We've gone from a 4-atom box to here we've got an 8-atom box. And look what's happened here in the middle is 6 atoms. So this is the energy of that wave function. Would you agree this is pretty much the same wave function, 6 lobes? Look how much the energy has dropped. And here this is 6 lobes, but now those 6 lobes are spread over 8 atoms and the energy's dropped. So that's kind of my goal. Not everything is a particle in a box, but if you understand the behavior of the particle in a box, you have an intuition for what's going to happen. When you increase the size of the molecule, your energy levels are going to get closer together. And they definitely did. Look how far apart those are. Those same 6 wave functions are down here now. And they're all very close together. Just because we've made the system, we haven't changed the size of the electron, the mass of the electron, but we've changed the size of the box. And these are the electron wave functions. So it's sort of confirmation that our intuition related to the way wave functions should operate is good, even from this simple one-dimensional particle in a box problem. Also, hopefully, this has explained to you the different shading we have on these things. So the green and the red, sometimes we'll might call this, positive and negative on our wave functions. But I don't want y'all ever to think that we're talking about charge. We're not talking about charge when we talk about the shading of those wave functions. It's like here we would label this positive and this negative, right? In terms of deflection, if we take a snapshot, we've got a positive piece and a negative piece. And when we're looking at a molecular orbital like this, the green shading and the red shading are deflections of the wave function. So that's a way to think of, maybe you should think of them as growing or shrinking. That's a better way to think about it. And so at some time this positive would be growing and this would be shrinking. Let me clean that up. That's a better way to think of the shading of the MOs. Shrinking. You all know what that is, right? So think of it this way. If we just have a hydrogen atom, or hydrogen, a p orbital. Let's do a p orbital, okay? So we typically draw a p orbital like this, and we might shade it, or sometimes we put a positive and a negative on there. That's not charge. That's this. So a p orbital is doing this. It's growing on one side while it shrinks on the other side, and then it grows on the opposite. So they swap color. And so it's just a snapshot in time. The colors are just a snapshot in time. And so when they're growing together, now let's put two p orbitals together. When they're growing together, they're overlapping. And when they're not, when they're out of phase, one's growing and the other's, out of phase with it, there's no bond there because that node is just moving back and forth, but there's no overlap between the p orbitals because the green and the red are touching and they don't interact. But if it's red at the same time, they grow, they overlap, they interact, and then they shrink back. So there's interaction of those. So thinking in terms of all of these funny shapes we have are just different pictures of waves, but they're three-dimensional waves. The hydrogen atom, which we'll get into, but the hydrogen atom, those solutions for that wave function are the spherical harmonics. So take a spherical shell and hit it with a hammer, and it's going to ring, okay? The classical solutions of that are the hydrogen wave functions. The ringing of that shell, which means sometimes the shell bulges on one side or the other, and that's a p orbital. Sometimes it bulges on the corners, and that would be a d orbital. Sometimes the whole darn thing expands and shrinks, and that's the s orbital. Okay, so it's the ringing of a spherical shell is what our hydrogen wave functions are. So that's all I have. What kind of questions can I answer to clarify things? Let me pull up the end result that y'all are aiming for in your projects, okay? Since we have a little bit of time, see if I can get this video to work well too with that. So, there's a small version and then there's the project version. So I'm not sure which one I'm bringing up here. But okay, this is the small version. Well, we'll walk through that one first. And window capture.
Replace our problem with the Schrodinger equation page.
Okay. Let me see if this will work for me. Can you all see the spreadsheet on me? No, you can't. There you go. So there's This is the small version. This is one that's going to be turned in as a quiz, as a homework quiz. Follow these panels piece at a time. And this will have you do everything in the big project, but on a really small scale. So maybe you want to do this one first, okay? And I'll check Blackboard to see that it's available. So what we have here is there's different tasks, right? And so we have we got this task to we've got the bond length, we've got the mass, and down here you'll plot the wave functions. So task 1 is the wave functions. In the empty spreadsheet, this is all empty. And it's just to sort of train you how to enter in the square root of 2 over L and so on, and referring to these different boxes. Here's the boundary condition L, here's the particle mass, and so on. And then you copy those wave functions down. You have them anchored. Let me double click. You have it anchored to this quantum number up here. And so then when you copy it over, it should be anchored to this quantum number. And so now we can plot those down here. And you can see we've got the n equals 2 and the n equals 3. If I come up here and change this to 1, it should update. And see, here we have n equals 1, and here we have n equals 3. And so we're looking at different quantum states. Then we can square those wave functions. And if we have n equals 1 times n equals 3, we square that. If we add all that together, the sum of that integral is equal to 0. If we look at this, this is wave function times wave function. See, it's this wave function times that wave function. When we sum all the way down, you have positive pieces, we have negative pieces, they cancel out, and we end up with 0. What about this one? This is the sum of the wavelengths, wave numbers, wave function squared. That's just this wave function squared. Sum that, it's equal to 1. That's the normalization piece. So instead of doing all that calculus that we did last time, Excel will do it for us. Square the wave function, add it together, times dx, that's the integral. We end up with 1 if it's a wave function times itself. If it's a wave function times any other wave function, like this column, you add it up, it's 0. We could have done this with matrix math here. And we can see that, let's just do 1 and 2 just for simplicity's sake. And we end up with, let's look at this matrix formula here. So it's the matrix multiplication of the transpose of this block of wave function. So that's the first piece. We take this block and we do transpose, it turns horizontal. And we multiply by this block of wave functions. So that first wave function row multiplied by the first wave function column added together times dx gives us the integral of wave function 1 times itself. And we get 1 in that square. Okay. What's this one? Well, that's the top row, which is wave function 1, times the second column, times wave function 2. Summed all together, dx, that's the integral of 1 times 2. And that's going to be 0. So we can see that Kronecker delta, vocabulary word, that's the diagonals are 1, the off diagonals are 0. We could also do it with sum product. We could just take the product of 1 times 1 or 1 times 2 or 2 times 2 and get that. So that's just normalization and orthogonality. Then we get into task 2, solving the Schrodinger equation. And this is where you were saying you're having maybe some difficulty. We need some constants up here and different units. So here's our wave function. 1, and let's do 1 and 2. And notice we've had to expand the box. That's discussed in the lab handout because we're doing centered derivatives. Now when we take the derivative, we need to take if I'm going to stand at this point and find out the instantaneous slope at this point, I'm going to take the next point and subtract the previous point and plot that slope right here on this point so that I'm not shifting anything. If I take the next one minus the one I'm at and plot it here, then I'm essentially shifting the curve to the left because I'm only looking forward. If I'm looking backwards, then I'm shifting the curve to the right. If I'm looking both left and right, I keep the symmetry of the curve. And so it'll cross zero at zero. So that's why we're doing centered derivatives. So the first derivative is here, and notice we lose a row. I can't calculate that derivative here because there's no previous point. So we lose a row and every time we take a derivative. You can see the active cells there. And so this is the first derivative. You see down here, it's the next point minus the previous point divided by the next x minus the previous x. And so then we take the second derivative. That's the Schrodinger equation, the second derivative of our wave function. And so now we've got everything inside the box. And so then we can take the original wave function times the second derivative wave function, integrate over all space. And so this is what we end up with. So here's our eigenvalues along the diagonal, and those are our Schrodinger equation values. So I have a little table that compares the numerical to the analytical, and you were talking about that. You have the analytical, because we have an equation for that. Here's the numerical. So we're just pulling those diagonal values from here. 77.2, when the analytical is 79.8. So that's the literature value, the analytical solution. We're doing numerical analysis, and notice we have 3% error. Why is it so far off? Yeah, so when you're taking the integral, you're basically drawing rectangles here and taking the area of that rectangle. And if your dx is too big, your rectangle corners that aren't below the curve are significant error. So what we're doing is we're taking a smooth function and we're turning it into a column graph, right? And the columns have a lot of little triangles that are either missing or overestimating the area under the curve. So this is an important concept in science and computation. It's called the fineness of your grid. So here we only have 10 points. That's a very coarse grid. If you want to do a fine calculation, it's going to take more computational resources because you're chopping your function into smaller pieces, and that's the fineness of your grid. This fineness can lead to numerical errors that give absurd results. Look at the wave function here, and we'll end with this. What if I go to quantum state 9? Look at my wave function. It's a little bizarre. What if I go to 10? It disappeared. What happened to my wave function? There's no error here. It's calculated, but it's 0 at every spot. It's because this oscillation function is hitting 0 at every data point. The fineness of my grid is not enough to capture the oscillation of this. I'm only plotting the nodes. So it's accidental that it's 0 because I'm getting my lobes, but they're between my data points, and my fineness of my grid has given me what is called an alias, an aliasing. If we go past that to like 12, it starts to behave. Oh, I did 21. Look at that, I did 21, and it's giving me an alias of 1. So it looks like n equals 1, but I'm at quantum state 21. And so that's what aliasing is. When you have a picture divided into small bits, those bits can give you a false image, and that's called aliasing. And we see that even in our monitors. You hear about anti-aliasing in your pictures. It's to get rid of pixel effects. Anyway, but that's where that term comes up. It looks alias. So numerical analysis can give you some problems related to the grid size. I'll just leave it at that. Y'all are going to be doing a pretty high resolution, 100 data points in your box. Your box is going to be 100, not 10. And you're going to go up to 15 quantum states.